details about this problem. We have two planes, and they're going to intersect. And my claim is they'll intersect along a line, provided that the planes themselves aren't parallel. Okay? So right off the bat, if you just give that some thought, I mean, if you had a plane like this, and let's pretend, here's the x, y, z axis. Okay, and you have this plane. This is a section of a plane floating up in space. And let's pretend this plane is parallel to the xy axis, right? I'm sorry, to the xy plane. Forgive me, right? So the xy plane creates the x and y axis together, create a plane. And I'm saying that this section of a plane is parallel to that. If I were to draw a second plane or second section of a plane that's also parallel to the plane created by the x and y axis, then those two planes, the black and blue ones, are parallel, and they'll never intersect. Okay? Now, as soon as I tilt one of these things, they're going to intersect. So I can draw a picture of something like that. So we have a section of a plane maybe that looks like this. It's sort of vertical. Maybe it's parallel to the YZ plane. And then another plane, maybe, that's parallel to the XY plane, sort of going back like this. This red section of a plane. And you can see that it's hitting that other plane along a line. Okay? And I think you can convince yourself that if you think of any two planes that aren't parallel, they should intersect along a line. It might always be nice to picture what that line looks like, or the slantness of that line, or the direction it's heading in, but you can convince yourself of that. Think of two walls meeting, right? The walls in the room that you're in right here. There's a wall here and a wall here, and then they meet in the corner, and that corner is described by a line, right? So our goal is this. We have the equation of two planes right here. Here they are. And our goal is to find the equation of the line of intersection of those two planes. Okay? I'm just going to copy this, go to a new page here. All right. So, before we can do that, we need to think about the equation of a line, right? So, in 3 space, our equation of our line looks like this. R of t equals some r0, which is a position vector, which is a point on the line, plus some direction vector, maybe we'll call it v, times a scalar t. So let's make a note here. T is a scalar. It's allowed to span through all real numbers. V is the direction vector of the line. And R0 is like a point the line goes through, or a position vector. I mean, the way it's written here, we're writing it as a vector form. We call this a position vector. But there you go. Okay. So if we're going to find the equation of the line of intersection, we need 2 things. We need to know what this R0 is and what the direction vector is. Okay? Okay. So I'm going to say that maybe it's a little bit easier to find this first. That's up to you. You'll decide when the problem's done. But R0 is a position vector, or you can think of it temporarily as like a point that has to be on both planes, because these planes intersect along a line. And what I'm asking for is, can we think of a point that would satisfy both equations, right? And once we've thought of that point would automatically have to be on this line of intersection that we're interested in finding. I can make that point into a position vector for myself. That's what I want to do. Okay, so how are we going to do that? Well, I guess first off, we can notice the following. We only have 2 equations, but we have 3 variables. Okay, so what that means is that there's multiple solutions that would work. Let's do a little bit of work here. I'm going to take that first equation for a minute, and I'm going to double it. So 2x plus 2y plus 2z equals 2. The second equation I'm just going to leave alone. 3x minus 4y plus 2z equals 1. Okay? And I don't know. Maybe we could do something here. I was thinking maybe we could cross out z. That's a possibility. Get a third equation. I don't know if that's all that helpful. It might be better to just do this. Let's just say that z equals 0. Suppose we let z equal 0. And if we did that, then the first equation would be this. X plus y equals 1. And the second equation is 3x minus 4y equals 1. Okay, so this wasn't such a bad thing. The stuff I wrote in green really isn't the best way to proceed. It's probably something you might think of doing on your own, but it doesn't help because you still end up with one equation with two variables. However, this is a little bit nicer. I'm saying, hey, let z be 0 for the time being, right? And let's see if we can solve for x and y. And we can, actually. I'm going to multiply this top equation by negative 3 maybe if you want. And it would become negative 3x minus 3y equals negative 3. And on the bottom, you'd have 3x minus 4y equals 1. And that's just a system of equations. I can add them together. If I do that, this cancels. I get negative 7y equals negative 2. Or I can say y equals 2 sevenths. Let's just check the algebra there. That looks good. Okay. Well, if y is 2 sevenths, I can take this first equation here. X plus 2 sevenths has to equal 1. That implies that x equals 5 sevenths. So I've done it. I found the point that's on both planes. The point is 5 sevenths, comma 2 sevenths, comma z was 0. That's how I started this whole story. Okay? You might say, why did I pick z equals 0? I just did it because it made things easier. It got rid of those terms. Okay? Now, if you want, you could temporarily just verify that this works. Let's recall, plane 1 has the equation x plus y plus z equals 1. Well, 5 sevenths plus 2 sevenths plus 0 equals 1. So there we go. That works. Plane 2, I think that was 3x minus 4y. Minus 4y plus 2z equals, let's make sure I got that one right, equals 1 also. Okay. We'll plug in the points and see how things go. So 3 times 5 sevenths minus 4 times 2 sevenths plus 2 times 0, or 0 is supposed to equal 1. Okay, so this is 30, what do we have? 3 times 5, 15 sevenths. Minus 4 times 2 is 8 sevenths. Well, that's when you subtract those, you're going to get 7 sevenths, which is equal to 1. Great. We have succeeded in finding a point that's on both planes. And I know that my line of intersection has to go through that point. So we're on our way. We can go back and look at our equation of our line and say, hey, I have part of that now. So I'm going to go write that. I'm going to say r of t is equal to 5 sevenths, comma 2 sevenths, comma 0, plus some scalar times the direction vector. So we're sort of halfway there. Let's write our equations of our planes again. X plus y plus z equals 1. 3x minus 4y plus 2z equals 1. Okay. And now we need to have our second realization. And this is the part, this is the whole trick to this question. Okay. So let's just draw a picture here. This isn't necessarily representing these two planes and what they would look like, but let's, I'll do my best here. Here's a section of a plane. Here's a section of another plane. There it is. And then I'll highlight in green the line of intersection. Okay. So what do we know so far? So far we have located a point on this line right here. You know, maybe it's there without any loss of generality. I'll just say that's the point we have. This is R0. That's the position vector pointing to that point. Okay, great. The thing I need to know, though, is the direction of this green line. I need to know what direction it's going in. And here comes the second really important realization to get this problem correct. Well, here's what we know. We know that our equations of planes come from the fact that it's the set of all vectors perpendicular to a given normal vector, right? So, and they also have to go through a particular point. So, if we look at just the blue plane temporarily, we could pick a point in there and say, hey, there's a vector coming up out of that plane that would be perpendicular to that plane at that point. Okay? And then we could do the same reasoning over here. We could say, hey, there's some point over here, And for this red plane, that is, this red section of a plane, we could say, hey, there's a vector coming out of there that's perpendicular to that red section of plane. Okay. Well, we actually know something about those vectors. Okay. We actually know, for example, temporarily, like the blue plane. Pretend this one's the blue one. Pretend this one's the red one. Okay. This vector here, this direction vector, has to be a multiple of the normal vector to plane 1. So I might as well just say, hey, let's just pretend it's the vector 1, 1, 1. Might as well, right? And we know that by looking at plane 1's equation. There's your normal vector right there. Okay, it's always ends up being the coefficients of x, y, and z. All right, so then in the same sense, or with the same reasoning, you know that this vector has to be in the direction of this vector, and we'll just call it that. We'll say that little back vector I drew that's perpendicular to the red plane is 3, -4, 2. Okay. So here's the question you need to answer. And if you can answer this question, then you're done with the problem. How is the direction vector of the green line of intersection related to these two normal vectors that I've drawn on the red and the blue plane? So the answer is that this direction vector of the green line is perpendicular to both of those normal vectors. Well, just to scan my memory for a minute. If I have two vectors, do I know a way to get a vector that's perpendicular to them? Yes, a cross product. That's right. So our direction vector v is going to be the normal vector to plane 1 crossed with the normal vector to plane 2. Okay? We can write that as determinant of this very special matrix, I, J, K. And then we have 1, 1, 1, 3, -4, and 2. And we're ready to go. So let's do this out. Right? It's going to be I times its minor, 1, 1, -4, 2, minus j times its minor, which is 1, 3, 1, 2, plus k times its minor, 1, 1, 3, -4. All right. So we're getting there. This is going to be, here we go. Let's see what we got here. We're going to have 2. We multiply these guys, right? 2 minus -4. So that's going to be 6. Here, we're going to have 2 minus 3, which would be -1, but then that's going to multiply by -j, so it's +1. And then you have -4 minus 3, which is -7. So there you go. That's the direction vector of the line. And we're ready now. We can say R of t is that position vector, 5/7, 2/7, and 0, which I think I made the comment already, but this could have been any point on the line. So there's lots of different things that could have gone in this first position. Okay? Plus a scalar times this direction vector. You know, if you had crossed the vectors in the other order, you would have gotten the negative of that direction vector. Okay? Any multiple of that direction vector is possible. It would still work. And there you go. This is called the vector equation of the line. Don't forget, you can write it parametrically. You can say x of t equals, y of t equals, and z of t equals. If we did that, we'd have 5/7 plus 6t. We'd have 2/7 plus t. And 0 minus 7t, or just -7t. Anyway, so that's that. Just a quick comment again about this direction vector. If you had crossed in the other order, your direction vector would have looked like this. Don't forget that this scalar spans through all positive and negative numbers, right? So that's why you're guaranteeing that you're not creating a ray, so to speak. There's nothing that says that t has to be just positive or something like that. All right, and then lastly, don't forget this is a symmetric equation to a line. You get that by taking this first one. You can say x equals 5/7 plus 6t, and you can solve for t. And if you did that, you get x minus 5/7 over 6 equals t. Well, you can continue to do that for each of these other components. And what you'd end up with is 3 expressions equaling t. Here would be the second one. Y minus 2/7 over 1, really. I don't need to write over 1, but I'll just show that. And then the last one is just going to be z over -7. equals t. And by the way, this one equals t also. So since all three of these expressions equal t, they equal each other, you can write this down. X minus 5/7 over 6 equals y minus 2/7 equals z over -7. And that's the symmetric equation of a line.